Hello students, in the previous lecture we have studied the simple harmonic oscillator. So in the simple harmonic oscillator we have assumed that the molecule obeys the law of simple harmonic oscillator so that it behaves like a spring. But as it behaves as a spring, it obeys the Hooke's law. But in reality, what happens? That the bond or the molecule does not obey the law of simple harmonic oscillation. That is what, here I will write it. Simple harmonic oscillation. Simple harmonic oscillator behaves as a spring. That is it obeys the Hooke's law. So now in reality molecule does not obey the law of simple harmonic oscillator. So as we know that if we pull or push the bond, what happens? It behaves as an elastic. That means example is, here is one atom, here is another atom. If we push them both, what will happen? They will get compressed. And if we pull them away from each other, they will get expand. So as according to that, we have said that it obeys the Hooke's law. But in reality what happens? It does not obey the law of simple harmonic oscillator. That means what? For small extension and compression, we can consider the bond as elastic. For small internuclear distances, it is considered as a elastic. But when we pull the bond at some point, it gets break and molecule dissociates. That means at point at which we pull or push the bond at extreme level, what happens? The bond gets break. That means molecule dissociates. Okay, so it will be more clear from this diagram. See, this diagram is internuclear distance versus energy. So according to the simple harmonic oscillator, what happens? This is a internuclear distance or the fixed bond length at which the energy of that molecule is 0. That means that molecule is stable. Either we contract that bond, that means we decrease the internuclear distance, its energy gets increases. That means it becomes unstable. Or we increases the distance, internuclear distance, that means the bond length. That means we expand the bond, its energy decreases. But what happens in reality that if this is an stable internuclear distance, we decrease the distance, nothing will happen, energy will increase. But when we pull the bond away from each other, at some level, what will happen? Energy will increase, and at some point the bond will break. Is it okay? So this curve is known as Morse curve. Morse curve. And the PM Morse has given the Morse function for the energy. So according to him, energy is equal to dEq into bracket 1 minus exponential of A into R equilibrium minus R, that we extend or we pull it, whole bracket square. This is the Morse function. Okay, remember, this is a Morse function. This curve is known as a Morse curve. This equation is Morse function. In this equation, there is a point A. A is a constant. A is a constant for a particular molecule. After that, dEq is a dissociation energy. So this was for the Morse function. So now, as we have considered that the molecule rotate, as well as now we are studying for the vibrational energy level. So according to the Schrodinger equation, the energy for anharmonic oscillator is given as epsilon nu is equal to nu plus 1 by 2 upon omega E bar minus nu plus 1 by 2 square omega bar E into Xe. This is expressed in centimeter inverse. So student, remember this formula for the anharmonic oscillator. Energy or wave number for the anharmonic oscillator. So in this equation, omega E bar is the oscillation frequency. It is an oscillation frequency expressed in centimeter inverse. Xe is the unharmonicity constant. So now we will rearrange this equation. So how to rearrange this? See, epsilon nu is equal to, solving the brackets, nu omega E bar plus 1 by 2 omega E bar minus nu square plus 2 into nu into 1 by 2, that will be nu, plus 1 by 4 omega E bar into Xe bar. So now what we will do? Nu omega E bar plus 1 by 2 omega E bar minus nu square omega E bar Xe minus nu omega E Xe minus 1 by 4 omega E Xe. Okay. Now rearranging it, what we will get? Omega E bar nu plus 1 by 2 into bracket 1 minus Xe into nu plus 1 by 2 bracket complete. So if you have to find that how it has come, you have to solve all this bracket and you will get the above equation. Okay, just what they have done, they have taken the common. See, in this, from this omega E into nu plus 1 by 2 is taken common, or that remains in the bracket. From this they have taken nu common, that means 1 minus omega e x e. So you will get it understand when you will solve this bracket, you will get this equation. Okay, try to solve it. So now comparing this equation, comparing the above equation with the equation of simple harmonic oscillator. So what we get, omega bar oscillation is equal to omega e bar into 1 minus xe nu plus 1 by 2. Why? Because the wave number equation for simple harmonic motion is nu plus 1 by 2 into omega oscillation. So now it shows that anharmonic oscillator behaves like the harmonic oscillator but with an oscillation frequency decreased with increasing nu. So what does this sentence indicate? That harmonic oscillator behaves as a anharmonic oscillator behaves as a harmonic oscillator. So when it will behave as a harmonic oscillator, when this omega oscillation will be equal to omega e, isn't it? So when these both will be equal, then it will behave as a harmonic oscillator. So what will happen, as the value of nu will increase, so this equation will become like this, nu e minus omega e x e nu plus 1 by 2. So when this factor will increase, it will multiply omega e, which will be subtracted from the omega e. That means the oscillation frequency decreases with the increasing nu. So hypothetical case we will discuss. Hypothetical case that nu will be equal to minus 1 by 2. So when this nu will be equal to minus 1 by 2, this will become 0, and as this will become 0, so omega e, that is the oscillation frequency, will be equal to the oscillation frequency of harmonic oscillator. That is omega e bar is defined here, as the equilibrium frequency or equilibrium oscillations frequency of the anharmonic system. The frequency for infinitely small vibrations about the equilibrium point, So that means what? Omega is defined as the equilibrium oscillation frequency of the anharmonic system. The frequency of for infinitely small vibrations about the equilibrium point. This is a definition for the omega E. So now the oscillation frequency for any real state specified by a positively charged integral nu, the oscillation frequency will be as follow. That is, omega oscillation will be equal to omega E into 1 minus 1 by 2 xe in centimeter inverse, and epsilon 0 is equal to 1 by 2 omega E bar 1 minus 1 by 2 xe centimeter inverse. We see that the 0 point energy differs slightly from that of the harmonic oscillator. So this is a 0 point energy for anharmonic system. Is it okay? The next is the selection rule. So which is the most important as point of exam. So the selection rule for anharmonic oscillator is delta nu is equal to plus minus 1, plus minus 2, plus minus 3 and so on. So here 0 is not included in the selection rule. That means what? All the transitions, that is from plus minus 1, plus minus 2, plus minus 3 are the allowed transitions. So one by one we will see. So when the transition is from nu is equal to 0 to nu is equal to 1. We know the formula for epsilon. The formula for epsilon is nu plus 1 by 2 omega E bar minus nu plus 1 by 2 square omega E bar xe bar. Is it okay? Now we know that epsilon or delta epsilon is equal to epsilon of nu is equal to 1 minus epsilon nu is equal to 0. So now putting the value of nu is equal to 1. That means 1 plus 1 by 2 omega E bar minus 1 plus 1 by 2 square omega E bar xe minus putting the 0, that means 0 plus 1 by 2 is plus 1 by 2 omega E bar. This minus will become plus 1 by 4. Why? 1 by 2 square there is. So 1 by 4 omega E bar xe bar. So now this is equal to 3 by 2 omega E bar minus this is 9 by 4 omega E bar xe minus 1 by 2 omega e bar plus 1 by 4 omega e bar xe. Is it okay? So now we know that 3 by 2 upon 1 minus 1 by 2 is 2 by 2, that is omega e bar, minus this 9 by 4 plus 1 by 4, that will be minus 8 by 4 omega e bar xe. So omega e bar minus 2 omega e xe. Taking omega e common, omega e bar into bracket 1 minus 2 xe. This is in centimeter inverse. So this change in frequency is known as fundamental frequency. Okay, this is known as a fundamental frequency. The second point is nu is equal to 0 to nu is equal to 2. Now again delta nu is equal to E nu is equal to 2 minus E nu is equal to 0. Is it okay? So now putting 2 plus 1 by 2 omega e bar minus 2 plus 1 by 2 square omega e bar xe minus 0 plus 1 by 2 is 1 by 2 omega e bar plus 1 by 2 square omega e bar xe. So now 2 into 2 plus 1 is 5 by 2 omega e bar minus this is 25 by 4 omega e xe minus 1 by 2 omega e bar plus 1 by 4 omega e bar xe. So now 5 by 2 minus 1 by 2 is 4 by 2 and 4 by 2 is equal to 2 into omega e bar minus 25 minus 1 is 24 by 4 omega e xe. Now 2 omega e bar minus 4 ones are 4 and 4 6 are 24. So now taking 2 common, 2 omega e bar as a common, what remains? 1 minus 3 omega e bar xe. That is 2 omega e bar 1 minus 3 xe. Okay, and this frequency or this change in energy or wave number is known as first overtone. This is a first overtone. Is it okay? The next point is the transition from nu is equal to 0 to nu is equal to 3. That is delta epsilon is equal to epsilon nu is equal to 3 minus epsilon nu is equal to 0. Now 3 plus 1 by 2 omega e bar minus 3 plus 1 by 2 square omega e xe minus 0 is there 1 by 2 omega e plus 1 by 4 omega e xe. Is it okay? So now this will become 7 by 2 omega e bar minus this will become 49 by 4 omega e xe minus 1 by 2 omega e bar plus 1 by 4 omega e bar xe. So 7 by 2 minus 1 by 2 is 6 by 2. So 6 by 2 is 3 omega e bar. Now this is minus 48 by 4 omega e bar xe. So 3 omega e bar minus 4 ones are 4 12 are 48. Omega E x E. Now taking the 3 common, 3 omega E into bracket 1 minus 4 x E. So this is known as a second overtone. This is known as a second overtone. So here I will write the first overtone was, fundamental frequency is equal to omega E bar minus 1 minus 2 x E. First overtone is equal to 2 omega E bar 1 minus 3 x E, and the second overtone is 3 omega E 1 minus 4 x E. So from the given value of the overtones or obtained value of fundamental frequency, we can calculate the value of oscillation or oscillating frequency. Is it clear? So now we will talk about the intensity of spectral line. We know that intensity of spectral line is given by the Boltzmann distribution law, that n nu upon n0 is equal to exponential of minus E upon kt. Now putting here the values, that is n is equal to n nu is equal to 1 to n nu is equal to 0. Here is the number of molecules present in the first vibrational level. This is the number of molecules present in the ground vibrational level, which is given by exponential of minus 6.63 into 10 raised to minus 34 into 3 into 10 raised to 10. Here the energy is in the order of 10 raised to 3 obtained for the vibrational energy levels, and K, that is 1.38 into 10 raised to minus 23 into 300. When we solve this, we get exponential of minus 4.8, and that value is 0.008. So this shows that nu is equal to 1 energy level is less or least populated. It shows that it is the least populated energy level. So as it is the least populated energy level, the transition from this level is very, very less. As there is no molecule present in this energy level, so how it will get transfer from that to another level? Here you have to remember, we have taken for the room temperature, that is 300 Kelvin. Okay. So from this energy level, this is not possible. That is from nu is equal to 1 to nu is equal to 2, or from nu is equal to 1 to nu is equal to 3. Why? Because nu is equal to 1 energy level is the less populated energy level. There are less molecules present in that level. But what will happen when we will increase the temperature? See, at 600 Kelvin, that is, we are doubling it, what we get, the spacing between the vibrational level is about 10 raised to 3 centimeter inverse. So at 600 K, n nu is equal to 1 to n nu is equal to 0 is become exponential of minus 2.4, which is approximately equal to 0.09. So as we are increasing the temperature, the level is getting populated. So at 0.09, the transition from nu is equal to the transition from nu is equal to 1 to nu is equal to 2 is 10% of the intensity of that of nu is equal to 0 to nu is equal to 1. So 10% of nu is equal to 0 to nu is equal to 1. So whatever the intensity is there for this transition, the 10% of the intensity is for this transition. Is it clear? Are you understanding this? So pay attention for this point. Now considering that nu is equal to 1 to nu is equal to 2 state if the transition is happening, that is delta nu is equal to plus 1. So what will happen to delta or change in E? That is 2 plus 1 by 2 omega E minus 2 plus 1 by 2 square omega E bar xe minus 1 plus 1 by 2 omega E plus 1 plus 1 by 2 square omega E xe. Okay. Now solving this, it becomes 5 by 2 omega E bar minus 25 by 4 omega E bar xe minus 3 by 2 omega E bar plus 9 by 4 omega E xe. So now we know that 5 by 2 minus 3 by 2 is 2 by 2, that is 1 omega E bar minus 25 minus 9 is 16. 16 by 4 is 4 omega E bar xe. So taking omega E bar common, what remains? 1 minus 4 xe. So this is known as hot bands. These are known as a hot bands. Is it okay? This weak absorption arises from the close to at slightly lower wave number than the fundamental frequency. Such weak absorption are usually called as a hot bands. Because why it is called as a hot bands? This is possible only at a high temperature. Why? Because as we will increase the temperature, nu is equal to 1 energy level will become populated. And as it will become populated, this transition is possible. Hence it is called as a hot bands. So student, you have to remember the first fundamental frequency, first overtone, second overtone and hot bands. Is it okay? Okay. So here I will stop. Thank you.